Hi everyone, welcome back. In this lecture we're going to look at how to calculate limits using what are known as the limit laws. So last time we looked at the definition of a limit, and then we looked at computing limits by essentially constructing tables of values where x was getting closer and closer to a, and then we looked to see what the function values were getting close to. Now we're going to look at a slightly more algebraic techniques for computing limits, ones that don't rely on a table of values. And the reason we want to do this is, well, it's motivated by the following example. Let's guess the value of this limit. The limit is t goes to 0, the square root of t plus 9 minus 3 over t. And let's just construct a table of values to see if we can get an idea of what the limit should be. So here I've just written the answer to about 6 decimal places. And what do we notice? As these t values get closer and closer to 0, these function values get closer and closer. Well, they seem to be picking up more decimal digits of 6s as we go down. And so these seem to be going to what value? Well, so as these go to 0, these seem to be going to, well, it looks like 0.16 where the 6 is going to repeat. So this is 1/6. So it looks like the value of the limit in this case will be 1/6, at least as far as our table of values has sort of indicated. Let's see how I actually constructed these values. I mean, you can use a calculator, but I would suggest using a computer. And so what I did was I just used an online computational tool. The link to this Sage Excel server is on our additional resources page. Or you can look to the URL just displayed here. And this just allows me to do some calculations within the window. The Sage is a computer algebra system, so a very robust computer algebra system in the background, and I'm just going to use it to do some calculations. So what I can do is I can input the function and ask it to work out some values. And so the first line, I've just defined the function. I've used sqrt as the square root function. In the second line, I've just asked it to work out the value of f.01. And this .n just tells Sage that I want it to answer in a decimal, and I want it to include only 9 decimal digits. So I'm just going to try to mimic what potentially your calculator is going to do here. You're going to work with probably 9 digits on your calculator. If it's more, well, you can always change this number to sort of mimic that. And let's just see what happens. So I can work out the value, and that's where I got the 0.1662206 from. I just truncated it there and got rid of the last few digits. Now we can work out the values for smaller values of t, so 0.01, and this is all I did to construct those table of values. So we can go 0.01, and suppose you say, well, okay, my table of values, I only got to 0.001. I want to go smaller. I want to see what happens if I go really small. Okay, so I'll take a lot of digits here of zeros. So this is 1, 2, 3, 4, 5, 6, 7, and then a 1. So this is 10 to the negative 8. And I see, okay, I've got a lot of 6s appearing here. Great, so I'll do even more zeros. Maybe the more I do, the closer it's going to get to 1/6. So that'll be nice. I keep going more and more zeros. And, oh, what happened? I lost a few digits of 6s. So let's go with another one. Another 0. Oh, I lost another digit of a 6. So maybe my original guess of the limit being 1/6 is actually incorrect. I've gone a little bit farther here, getting closer and closer to 0, and the number's doing something different. Okay, so let's just see keep going and see what happens. Oh, 0.4. Oh, so my original guess seemed to be way off. Wait a minute. Now I get an answer of 0. Is the limiting value really 0? What's happening here? How do I know what to trust? How do I know if it was going to be 1/6? How do I know if it's going to be 0? This is the issue with using a table of values, is sometimes things happen like this where you're left wondering, what is the answer? What happened? Well, I'll tell you what happened here. What's going on is we're taking this difference. We're taking this thing minus this thing. When t is really, really, really small, t plus 9 is really close to 9. So when I square root it, this number is really close to 3. Now imagine you're using 9 decimal digits. So you've square rooted this small number plus 9, you get a number that's really close to 3. Maybe it's 3 point, and then you got a lot of zeros before you get the next non-zero digit. What your calculator computer is going to do is it's going to look at the 3, see a long string of zeros before you get to a non-zero number, and it's going to say, well, if you're only working in 9 decimal digits, the 3 is much more significant than the rest, so it's just going to drop the rest. It's going to drop the rest. And so this being really close to 3, your computer or your calculator will round it to 3. And then we take 3 minus 3, that's 0. So it's a rounding issue that causes that problem. If we take t even smaller, so the issue here was when we took t really, really small. I don't know how many digits decimal digits it was. It was probably around 10 or 13. So 2, 4, 6, 8, 10, 12, maybe something like that. We got an answer of 0.000. In other words, we got 0 for our answer. And it was a rounding issue. So we have to be very careful when we do these table of values. These rounding issues can come up. These approximations could cause flaws in the values that we're trying to have come out. So the key here is that our computer returned an approximation. Which was, in some sense, it was wrong. So there was a rounding error here. Okay, so what this means is we need better methods. We need better methods to compute limits than just relying on a table of values. That's what this section's about. It's how to get these better methods. So let's look at what these methods are. For the statement of these results, let's just assume that the limit of f and the limit of g as x goes to a both exist, and c is just some constant. Then if I take the sum of two functions and I work out the limit as x goes to a of the sum of those functions, then that's just equal to the sum of the corresponding limits. So I can compute the limit of a sum by just working out the limit of the individual pieces and then adding them. Same is true for differences. This multiplication by a number, constant. Multiplication of two functions. If I want to compute the limit, I just need to do the individual limits and then multiply them. Same with a quotient. The limit of a quotient is the quotient of the limits provided the denominator is non-zero. That's a key point here. So if I want to work out the limit of a quotient, then I can work out the limit of the top and the limit of the bottom. Provided the bottom's not 0, then I get my limit. If the bottom is 0, we have to do more work. And that's going to be the main focus of the kinds of examples we work on. What happens when the denominator is 0? What's the more work we have to do? And similarly, if we take the limit of a function raised to a power, we can just work out the limit of the function and raise that result to the corresponding power. These limit laws are proved in Math 232, or sorry, 242, in our real analysis course, Math 242. So we're going to assume these are true and we're going to run with them and use them in this course. If you want to see why they're true, they really go back to sort of a rigorous definition of a limit, and these kinds of questions are dealt with in a course such as Math 242, Real Analysis. So here's a couple more special limits. The limit as x goes to a of a constant is just the constant. So in other words, as x gets close to a, what does c get close to? Well, c is not changing, so c stays close to c. As x gets close to a, what does a get close to? Well, x gets close to a. It sounds redundant. As x gets close to a, x gets close to a. And in some sense it is redundant. But that's the way it's phrased in terms of a limit. Limit as x goes to a of x is equal to a. And using these two limit properties, special limit properties, as well as the more general ones above, we can start working out values of limits rather quickly. So let's evaluate this limit. The limit as x goes to 2 of this polynomial, well, I can use the property that we have above that tells me that if I want to work out the limit of a sum, I just need to work out the sum of the individual limits. So this means I can work out the limit of the first plus the limit of the second term minus the limit of the third term. This one was actually using the second property. Limit of a difference is the difference of the limits, property B. And lastly, we have the limit as x goes to 2 of 5. Now what can we do? Well, I have this property f that tells me the limit of a function raised to a power is just the limit of the limit of a function raised to a power. I just need to work out the value of the limit of the function and then raise that result to the power. So this is the limit as x goes to 2 of x all cubed. This is, I can pull the constant out. I can pull the square out in some sense by just squaring the resulting limit. And similarly down the line, pull the constant out, the limit as x goes to 2 of x. So I'm just using these properties of limits that we have above. Actually, I'll leave the 5 inside. Could take it out, could leave it. Just using the properties of limits to rewrite it in this way. Now, we can use those special limits. Limit of a constant is just itself. So that means this is a 5 back here. The limit of x as x goes to a is just the value of a. So as x gets close to 2, x gets close to 2. So the value of that limit is 2. And then the value of this limit is also 2. And then we've got the square there. And the value of this limit is also 2. So we got the cube there. And so this becomes then 8 plus 12 minus 8 plus 5, which is 17. So there's the value of the limit. Now you may be looking at this saying, wow, that was an awful lot of work to evaluate the limit. Well, in some sense, we just wanted to establish how to use these limit properties. So give an example of how to use these limit laws and work them out in great detail to see what the value of the limit is. But now we can see we don't always need to do all these details. Really what happened is we started with this limit. And if I jump down to this step, we see all we did was just pop x equals 2 in everywhere you see an x. So we were able to evaluate this limit by just directly evaluating the function at 2. Now this can work in some cases. We'll see cases where it doesn't work, but in some cases this direct evaluation of the function at the value of a, in this case 2, is how we can work out some of these limits. In particular, this is known as the direct substitution property, and it says that if we're staring at a polynomial or a rational function and a is in the domain of f, so it's not a place where the denominator is 0, then we can work out the limit by just directly evaluating the function there. Okay, so let's do a bunch of examples. Let's find the following limits. Limit as x goes to -1 of x plus 1 over x cubed plus 1. So first thing we do is we try to see, can I plug -1 into this? And if I plug -1 into the top, I get that that becomes 0. If I plug -1 into the bottom, -1 cubed, that's -1, plus 1, that's 0. Oh, this is a problem. -1 is not in the domain of this rational function. So I can't use this direct substitution property above. And notice that the limit law says I can't even take the limit of the top and put it over the limit of the bottom because the bottom is 0. I can't divide by 0. So this is that case where I mentioned that we have more work to do. We've got 0 over 0. I want to know what do the values of the function get close to as x gets close to -1. I'm not asking what's going on exactly at -1. At -1, the function is not defined there. I'm just asking what the limiting value is. What's going on with the function values when x is close to -1. So here's what we do. We try to see if we can simplify this function in some way. And here we're guided by the fact that -1 is both a 0 of the top and a 0 of the bottom. So that means x plus 1 is a factor of the polynomial on top, and it's a factor of the polynomial on the bottom. I know I can factor an x plus 1 out. The question is what's left over. So how do we get to what's left over when we do this factorization? Well, I can take x cubed plus 1, and I want to factor out an x plus 1 from it. So this is sort of our side note here. I'm going to do a bit of factoring. I can do some long division here. X goes into x cubed, x squared times, so that's x cubed plus an x squared. So I multiply the x squared by the x plus 1 to give me that. Now I take the difference, and that becomes a negative x squared plus 1. How many times does x go into negative x squared? It goes in there negative x times. So that becomes a negative x squared minus an x. And again, I take their difference, so that becomes an x plus 1. And x plus 1 goes into x plus 1 once and has nothing left over. So this is the piece that I'm missing. That's the factor, x squared minus x plus 1. Now what can I do? Well, this is the limit as x goes to negative 1 of, it looks like I can cancel off the x plus 1s. They're both a factor of the top and a factor of the bottom. So this becomes x squared minus x plus 1. Now there is a subtle point that we need to keep in mind here. This function, the x plus 1 over x plus 1 times x squared minus x plus 1, this function here is not the same as this function here everywhere. This function here, the 1 over x squared minus x plus 1, that one's defined at negative 1. I can plug negative 1 into this and work it out. It's defined there. Negative 1 is in the domain of this one. Negative 1 is not in the domain of the one above. Does that matter? Well, in fact, that's the whole reason this works. So what we've found here is that these functions aren't the same, but their limits are the same. Why are their limits the same? The limit only cares about what's going on around x equals negative 1, not at x equals negative 1. These two functions, so this equality here for these limits is valid because these two functions, x plus 1 over x plus 1 times x squared minus x plus 1, are equal. So this one is equal to x squared minus x plus 1, precisely if x is not equal to negative 1. They are equal. These two functions are equal when x is not equal to negative 1. The only issue happens when x is equal to negative 1. The second function is defined, whereas the first one isn't. But that's to our benefit, because if these two functions equal everywhere except negative 1, then their behavior around negative 1 is exactly the same. What's going on at negative 1? Well, this one's defined, so I can use it to evaluate this function at negative 1 and get what this function is close to. So I'm going to pop negative 1 into this rational function. Negative 1 squared minus negative 1 plus 1. So that's 1/3. And there we go. So I took my original rational function, which wasn't defined at negative 1. I found an equivalent one to it, which is equal to it everywhere, except at negative 1. But this one is now defined at negative 1, so I can use it. Pop negative 1 into that, and I get the value of the limit. So here's a visualization of this. So I've got my function x plus 1 over x cubed plus 1. There it is. That's what it looks like in red. Notice that it's not defined at negative 1, so there's a hole there. What I did was I found an equivalent simplified expression for this one, except that this simplified expression has eliminated that problem at negative 1. So notice that the function g and the function f agree everywhere except where there was a hole for the function f. That hole is filled by the function g. And so if I want to know what the limit is for the function f as x goes to negative 1, I just have to focus on my function g and evaluate it there at negative 1 because it's got that hole filled in. That was the key. That's what we did. We took the original function, simplified it to a function where the new function has a slightly bigger domain and in fact allows us to compute the limit by direct evaluation. Let's look at another example. This one is the motivating one where we used the table of values to try to construct the limit, and we got those sort of contradictory bits of data. Was the limit really 1/6, or was it 0, or was it something else entirely? Let's see how we can actually do this. So again, just as a first step, always just try to see what happens if you plug t equals 0 in. So this goes to 0 plus 9, so that goes to square root of 9, 3 minus, so the top goes to 0, 3 minus 3. The bottom goes to 0. So it's a limit of type 0 over 0. I can't directly evaluate it then in this way. I have more work to do. The more work to do is to try to figure out how to cancel something from the top and bottom. Since t is going to 0, the bottom goes to 0, there's a factor of t in the bottom. There might be a hidden factor of t in the top. If I can get that hidden factor of t in the top to show itself, I can cancel with that factor of t in the bottom and eliminate that 0 over 0. So my goal here is to try to get access to that hidden factor of t in the top. And the way we do that is we're going to try to, well, we're going to rationalize the numerator, but what that means is we're trying to get rid of the difference of the square root and the 3 in the numerator by replacing it with its conjugate, the square root, and then a plus 3 in the denominator. So I'm multiplying by 1 in a fancy way here. This is multiplication by 1 in a fancy way, a common trick to do these kinds of simplifications. Multiply by 1 in a fancy way. Now when I expand out the top, I get the square root of t plus 9 times the square root of t plus 9, so that's just a t plus 9. I get these cross terms, this 3 times the square root of t plus 9 and a negative 3 times the square root of t plus 9. Those cancel off. So all I'm left with is the final term, negative 3 times 3, so that's negative 9. What's on the bottom? A t, a square root of t plus 9 plus 3, and now we see that hidden factor of t that I was talking about in the numerator. The 9's cancel off. That leaves me with just a t in the numerator. Let's write it out here. T goes to 0. T over t times square root of t plus 9 plus 3. There's that hidden factor of t in the numerator. We can now get rid of it. Now there's this question of, if I cancel it off, do I really get the same limit? Because I've got this new function now. I've got this new function here, 1 over the square root of t plus 9 plus 3. That new function is different than this function. How is it different? Well, they agree everywhere except the second one now is defined at 0. So they're actually not the exact same function. This one is defined at 0, so it's got a slightly bigger domain. But that's to our benefit again. These agree everywhere except at 0. So their limits are equal at 0, because the limit only depends on what's going on around 0, not exactly at 0. So their limits are equal. This second one, I can work out the value of its limit by directly substituting in 0 into the expression. So that's 1 over the square root of 9 plus 3, or 1/6, and there is our answer. We thought the answer was 1/6 using our table of values, but then we went a little bit further and got slightly perturbed by the fact that these things might have been going to 0. But now we see that the actual value of the limit is 1/6. And we got it through these algebraic means. So let's look at this next limit. So you might notice that this limit is the kind of limit that we had crop up when we were studying the tangent line problem. So this is really asking a question about, we've got this function f of x equals x squared. At a particular point x, we can construct the corresponding tangent line there. And the question is, what is the slope of the tangent line there? Well, the slope is given by this expression. So that's really what we're working out here. We're working out the slope at this arbitrary point, x, f of x, or x squared. So here we can use the fact that we know what f is. It is the squaring function. So this is x plus h all squared minus x squared all over h. This is the limit we want to work out as h goes to 0. So this is the limit as h goes to 0 of x squared plus 2xh plus h squared. So I've expanded that first square minus an x squared all over an h. You can get that these x squareds cancel off. This is the limit as h goes to 0 of 2xh plus h squared all over h. Now I've got this common factor of an h in top and bottom, and then I can cancel those off. And so this becomes the limit as h goes to 0 of 2x plus h. Now what are we taking the limit with respect to? We're taking it with respect to h. So for all intents and purposes, I can think of x as just being a constant here. As h goes to 0, all I'm left with is 2x. So what we've just found here is that the slope of this tangent line at whose x-coordinate, who passes through the point whose x-coordinate is x, the slope is given by twice the x-coordinate, 2x. And that's true for any x value, any point on the curve. We know the x value, we go up to the curve, we can figure out the slope of the tangent line just by multiplying the x value by 2. So there's our limit of this expression. Let's look at another example. Find the limit as x goes to 0 of x squared over absolute value of x. How do we do that? Well, there's a reminder here. The reminder says that you can work out the value of a limit by working out the left-hand limit and the right-hand limit. And if you get the same value for both the left and the right hand, then the general limit is that common value. Now, why is this reminder here? Well, it's here because of this absolute value of x. When x gets close to 0, it depends. Are you coming to 0 from one side or the other? And so maybe we should treat those independently. So we'll first consider the case when maybe x is bigger than or equal to 0. So in that case, we're looking at the limit as x goes to 0. If it's bigger than 0, we're coming at it from the right. X squared over absolute value of x. So let's look at this limit. Maybe I shouldn't say if x is bigger than 0. Maybe I'll just say 4. So this is the case we're considering, for x bigger than 0. Look at the right-hand limit. What's happening in this case? Well, if x is positive, then taking its absolute value does nothing to it. So I can always replace that with x itself. Here we're using the fact that absolute value of x is defined to be x if x is positive and negative x if x is negative. And we've just used that first piece there. So this becomes the limit as x goes to 0 from the right of x, which is just 0. We can do the same thing for negative values of x. In other words, we're coming to 0 from the left. In this case, I can replace absolute value of x with just negative x. Because when x is negative, the absolute value of x is equivalent to negative x. And so this becomes the limit as x goes to 0 from the left of negative x, which again is 0. So these two things match each other. The right-hand limit and the left-hand limit are both equal to 0. So therefore, in general, so the general limit, the limit as x goes to 0 of x squared over absolute value of x is 0. Okay? So we did this one by first splitting up the absolute value of x into its piecewise defined form, and using each piece to work out the corresponding right and left-hand limits, noticing they're the same, and getting, therefore, the general limit, the general two-sided limit as 0. There is an alternate way to do this, and it avoids having to consider these pieces, and so it might be worthwhile noticing this alternate way. I want to look at the limit as x goes to 0, x squared over absolute value of x. What I could do is I could notice that x squared, well, that's a positive number, so it's actually the same as the absolute value of x all squared. Absolute value of x all squared and x squared, they're equivalent. Now I can factor one of the absolute value of x's from the bottom with one in the top, and I get that this is equal to the limit as x goes to 0 of just the absolute value of x, which is 0. And in this case, I got the same answer, but I didn't need to consider the left and right hand limits. I just did a general limit, general two-sided limit. So let's look at some properties that limits have. This first one's known as the comparative property. Suppose I have a function f, which is smaller than the function g. It doesn't have to be smaller than it everywhere, just near a. So maybe a is somewhere around here. So f is smaller than g, smaller than or equal to g. What can we say about their limits? Well, the limiting value of g has to be bigger than the limiting value of f. So if g is bigger than f, then the limiting value of g is bigger than or equal to the limiting value of f. Or in other words, another way to say that, if f is smaller than or equal to g, then the limiting value of f is smaller than or equal to the limiting value of g. And it's just coming from sort of a picture like this. So we have this conclusion. This comes in handy, in particular, when you can find bounds for a function above and below, bounds which are easier to work with than the original function. So here is a result known as the squeeze theorem. The main point of this is, suppose I want to find the limiting value of g as x gets close to a. Well, if I can take functions that I know something about and bound g above by one of the functions and below by the other one, such that the limiting value of f and the limiting value of h are both L, in other words, the function above and the function below head to the same place, then I conclude that g must go there as well. And again, here's a picture. So h maybe looks something like this. F is smaller than h, but it's going to have the same limit. So it might do something like this. It's got the same limit. So they both have this limit, limiting value L at a. So again, this one was f, and this one was h. G is trapped between f and h near a, so it does something like this. Now if it's trapped between it, there's only one place it can go. It has to pass through that same value. So as x gets close to a, g must also get close to L. So there's g. This is how we're going to use this comparative property. We're going to say that I want to know the value of the limit of g, try to find functions above and below g that you can work with, find their limits, show their limits are the same, and therefore g is trapped between it. It must also pass through that same point, have that same limit. This is the squeeze theorem. So in some sense, g has to be squeezed between f and h. F and h are going to the same place, and if g is trapped between them, squeezed between them, it must also get squeezed through that same place as well. Let's look at an example of this. Let's show that the limit as x goes to 0 of x times sine of 1 over x plus cos of 1 over x is 0. Now here's the thing. Whenever you're working on a limit, the first thing you want to do is just try to see what happens if I evaluate the function at the point. So as x gets close to 0, well, I can't divide by 0. Okay, well, I can start to think about what happens. 1 over a number getting close to 0, that will either be a really big positive number or a really big negative number, depending on whether x is close to 0 through the positive values or through negative values, from the right or from the left. Sine of a really big positive number, well, that can be anything, because sine just oscillates between 1 and negative 1 all the way along. Similarly, cos oscillates between 1 and negative 1. So as x gets close to 0, sine and cosine are just bouncing around, bouncing back and forth between 1 and negative 1. They're not settling down. They're not getting close to any particular number. But x is going to 0 as x goes to 0. So this first piece is going to 0. This second piece, well, the limit doesn't exist. So the question is, how do I deal with this? Well, I'm going to try to show that the limiting value is still 0. It's still 0. How do we get that? We're going to try to use the squeeze theorem. And the very first thing to notice is that sine of 1 over x is trapped between 1 and negative 1. I already mentioned this, but we're going to write it down explicitly because we're going to use it. Cosine of 1 over x is always trapped between 1 and negative 1 as well. So if I add them up, sine of 1 over x plus cos of 1 over x, that's trapped between negative 2 and 2. Now what I want to do is I want to multiply by x, because that's really the function I'm trying to study. So if I multiply through these inequalities by x, Well, I have to be careful. I will change the direction of the inequality if x is negative. So we're going to consider a couple of cases. For x bigger than or equal to 0, we can multiply through these inequalities by x itself, and I don't have to change the direction. So this is x times sine of 1 over x plus cos of 1 over x is less than or equal to 2x. I've got the function I'm trying to find information about trapped between two other functions. What happens as x goes to 0? Well, as x goes to 0, this first function, negative 2x, that gets close to 0. The limiting value is 0. The limit as x goes to 0 of 2x over here, that's 0. So both the function below and the function above are heading to 0 as x goes to 0. So the thing trapped between them must also go there as well. So here's how I'll write that. Limit as x goes to 0, negative 2x, has to be below the limit as x goes to 0 of the function we're interested in, sine of 1 over x plus cos 1 over x, and that's below the limit as x goes to 0 of 2x. Notice I'm just using that comparative property of limits twice now. The function here on the left is smaller than the one in the middle, so the limit has to be smaller. And similarly for the other inequality. This is 0. The limit as x goes to 0 of negative 2x is 0. So that means this limit is both bigger than 0, bigger than or equal to 0, and smaller than or equal to 0. So therefore, it must be equal to 0. There's only one number that's both bigger than or equal to 0 and smaller than or equal to 0, and that is 0 itself. So the limit as x goes to 0. Oh, I need to be careful here. I'm assuming that x is positive, so my limits aren't general limits here. I'm coming to 0 from the right. When x is positive, I had to make that assumption so the inequalities didn't switch around, but I also have to carry that through on my limits. So this limit as x goes to 0 from the right of x sine of 1 over x plus cos 1 over x is 0. So that's our right-hand limit. We wanted to show that the general limit was 0. So we need to do the same argument for the left-hand one. For x less than 0, less than or equal to 0, I can multiply through this inequality by x, but since x is negative, I have to switch the directions of the inequalities. Now that's sine, so it's x times sine of 1 over x plus cos of 1 over x and 2x, switching the directions of the inequalities. And then by a similar result, we take the limit. So now the calculations are pretty much identical to the one above. By a similar result, we work out the left-hand limit. Both functions above and below the one we're interested in are heading to 0, so the thing trapped between them must also head to 0 in the limit. So this is sine of 1 over x plus cos of 1 over x is 0, and therefore right-hand limit is 0, left-hand limit is 0, so the limit in general is 0. And we've now shown it. Now, one thing I should note is I did use the squeeze theorem here, so we have to make sure we indicate that in our argument. Where did I use it? The inequality on the functions. We then worked out the limit. This was by the squeeze theorem here. And similarly, we had it as well down here by the squeeze theorem. It was essential for us to work out that upper bound and that lower bound on the function, both of which we can work out the individual limits, so we got information about the one trapped between. Now, if we look at the graph, it should be a little bit more clear about what went on here. So the blue curve is the one we're interested in. I want to know what the limiting value is as x goes to 0. This pink curve is that line y equals 2x. When x is positive, the pink curve is above our function. The orangey, sort of yellowy curve here, that's negative 2x. When x is positive, it's below the curve. And so what that means is our value, for any x value, the value on the function is trapped between the two values, one on the pink curve, one on the orange curve. And those two curves, the values on those two curves, are heading towards 0 as x gets close to 0. And so the point on the blue curve, being trapped between them, must also go to 0. Now, why we had to consider two cases was now if we look at the negative x-axes, we see that for those x values, it's the negative 2x curve that's on top and the 2x curve that's on the bottom. They switched here. That's why we needed to do these two independent cases. On one side of the y-axis, for positive x values, 2x was above, negative 2x was below. But on the other side, negative 2x was above, and 2x was below. But the same argument still holds. The values on those two lines are going to 0, and so our function value must also go to 0. And so this is the squeeze theorem. This is the visualization of it. You want to try to find an upper bound and a lower bound on the function such that those two functions have the same limit, so the thing trapped between them also has the same limit. All right, that's it for this section. Thanks very much for watching, and we'll see you again next time.